Good morning. Today is November 24th, 2018, and this is the John Chappell Natural Philosophy Society Science Chat. I'm your host, Franklin Hu, and we invite you to join our society at naturalphilosophy.org, where you can join us and get various member benefits. You can also find us on social media on Facebook, and we have our own wikis. You can also find recordings of this conference for playback on youtube.naturalphilosophy.org. And if you would like to help us out, please join us on the CNPS Basecamp at hq.naturalphilosophy.org. We could always use help in organizing and promoting the group. And our upcoming conference is on June 26th to the 29th. It's here in Seattle at the University of Washington. And our keynote speaker is Dr. Daryl Pollack. He'll be talking about the fourth state of water and scientific activism. So after a 3-week absence, I have returned, and today I was thinking to talk about the topic of quarks, whether those things are fact or fiction. So I did have one book on the topic here called The Hunting of the Quark by Michael Riordan. Although, like many physics books, reading through this, it's kind of hard to see, in spite of the thickness here, what are the actual reasons for thinking that these quarks things exist. So to start off with, I'll give you what my opinion is on the topic, and that I believe that quarks are in fact a complete fiction. They don't exist, they've never existed, and is perhaps one of the most major wrong turns that physics has ever taken to believe that these quarks, which are fractionally 1/3 charged objects, actually exist and have some reality. Now, if you read the book, a lot, like half the book is just the basic background history of them discovering all of these new particles in accelerators, and there's like, they called it like the particle zoo. I mean, it's just like, I don't know how many, like in the hundreds of different particles. And so quarks were invented to try and categorize what they're made out of, kind of thing. So based on this, having fractional charges and things like that, they're able to take the particle zoo and then categorize it and say that, okay, this particle is made out of this many type of quarks and so on. So that's and they've been able to like categorize every single particle they've ever found using this scheme, right? Although even at the time it was invented, people are thinking, well, this is more of a convenient taxonomy kind of thing rather than anything that's actually real, right? Because you can sit there and categorize it by certain categories, and call certain people belong to, like, to say the wolf family, certain ones belong to the zebra family, certain ones, kind of thing like that. But although, in recent times, mainstream has adopted these things as real things, which like I said, I believe is patently false. Okay. Now, the reason why I believe this is because, basically the hierarchy doesn't seem to make any sense, because my main question is that if quarks exists, then how does, say, the electron fit into all of these things? Because an electron is an entirely different particle from anything else. In fact, it's the only particle which doesn't appear to be made out of quarks, right? So how is it you can explain all the other particles like protons, neutrons, and J-pasons, and charm lambda, blah, blah, blah. but you can't explain what the electron is, right? That seems like a gigantic hole in the theory. That you say you have a theory that explains everything, but you can't explain the electron, which is definitely exists. And we definitely know its properties, but yet it can't be explained under quark theory. So I would first of all completely disregard and blow away the claim that quark theory can explain all observed particles simply because it can't explain an electron, right? Electron is just like everything that's made out of quarks over here, and then we have the electron, right? So that would be one reason why I would think that the quark theory is grossly inadequate for explaining things. So I see Harry has written the raised the flag. Yes, and if you have any questions, just feel free to chime in there. So Harry, did you have a comment?
Yeah, I had a comment on, you're making a lot of assumptions. One is you use the word explain as if the purpose of physics is to explain things. And I don't think that's what they think they're doing. They're only creating models.
Well, that may very well be true. Me personally, I'm trying to explain things, so that may explain the difference.
Well, perhaps you need to define what you think science is. I think that's, you know, and every time I hear you talk, you sort of, criticize mainstream, and you talk about explaining things. That word explain has different interpretations. So it would seem to me that mainstream thinks that they've created models that, as long as the models are consistent and they can do experiments and the experiments are consistent with the model, then they've explained things.
Yeah, so that's different. I was trying to say that even in the early development of quark theory, even the people who, like the inventor himself, was not sure whether the quarks had any physical reality or whether they were just a convenient accounting mechanism, right? Now, physics, you're saying they're perfectly fine if they've come up with a convenient accounting system for explaining the observed particles, whether or not they exist or not. And some people feel that way, and I strongly feel that is another gigantic wrong turn in philosophy. That's basically where we disregarded logic and the desire to actually figure out physically what's going on. So that could, that's an interesting point. But
well, back to your point about the electron, it seems to me, I don't see Bill Lucas is here. Bill Lucas has repeatedly commented that an electron has 3 structures in it, and that they do experiments and they can see the 3 structures. Okay.
No, actually, they can't. There is actually, to my knowledge, and I've looked at all of Bill's stuff.
Well, he's not here to defend his position.
No, he's not. But I've seen all of Bill's stuff, and basically all of that stuff has to basically be postulated.
Because there he is. I see Bill Lucas now.
Okay, well, Bill can comment on that. So whether
your first claim was, as I understand it, okay, so we dispense with the explain issue. So basically, mainstream is only creating models, not necessarily reality. And all the models have to do is be consistent with the experimental evidence. And
yes, that's correct.
Now, notice that, what a lot of the people in these discussion groups and the discussion threads that have been going on, they want something called reality. And it's assumed in science that experiments can lead you to reality, but I think that's a false assumption. I don't think the experiments necessarily can rule out all the possible theories that you can have, and I think we see that in our discussions. But mainstream doesn't deal with that issue of or they assume that experiments produce uniquely true models. Okay, that's, in my opinion, what you should be criticizing. And, so they assume that their model, which they call I forget, the standard model, that's what they call it. They don't even use the word theory, they call it standard model, okay, which makes it even more clear. Okay, now their assumption is that somehow that standard model is uniquely true, although they've got all these fudge factors in it. So the assumption is that experiments, physicists doing experiments, produce some kind of a unique interpretation of reality, when in reality, I doubt that that's true. But having said that, your criticism is that quarks aren't part of electrons. That's your second criticism, correct?
No, my criticism is that quarks can't explain electrons. That electrons are not constructed of quarks, even in mainstream quark theory. So what are they? They don't fit. They can't be explained.
Okay, what does the book say that you are referring to, that you're using as the basis for your criticism?
Well, I mean, I would say that the book
is silent on that issue or not.
That they don't mention that as being a gigantic issue. They just sort of paper over that and not explain that. Well, yeah, a neutron is this, a proton is that, charm sigma is this, but they never explain what the gaping hole.
So what he does in his book is essentially, quarks are essentially basically a theory of baryons, and electron is a lepton, and that's a different animal altogether.
Yeah, exactly. I think that's how they get around it. They say these are baryons, and then we have lepton, which is.
All right. Well, I don't really understand the standard model that well, so I can't comment on that. Oh,
I mean, it just logically, even as a casual bystander, you can see that we have a theory that doesn't explain the electron as a lepton. You've got these things made out of quarks, and then you have this electron here, and it's not explainable by that. So what you do, you just relabel that whole thing as something else that you don't have to explain. But then you're still not explaining what all particles are made out of, right? I mean, I think if you have a good theory of how all particles are made, you ought to be able to explain the electron. Not unless you think the electron is absolutely fundamental, in which case you don't have to explain what it is.
Well, all right. Well, I guess I'm not that familiar with the standard model. I'm not really sure exactly what the mainstream way of explaining this, what you'd consider to be a contradiction away. Maybe somebody else can comment on that.
Well, like I said, I've read some of these books and stuff, so I'm trying to, based on what I've read, trying to explain to you how the standard model works. So,
from what I've read, I think they say leptons are fundamental particles in their own right, and hadrons are made up of quarks, and quarks are fundamental particles in their own right. I think that's how they get over it.
Yeah.
But as far as I can see, the whole thesis is based on the scattering types of experiment. I mean, that were really started by Rutherford, where from the scattering results, he said, well, the atom cannot be one indivisible unit. It must have maybe a nucleus and then electrons and so on. That's how the atomic model, the Rutherford model, came. And they've repeated these experiments, and they found, okay, if you irradiate baryons or something like that, you get scattering, and therefore there must be particles which are smaller than the baryons themselves. But this doesn't occur with leptons. Now, presumably, if they have further experiments which do show such scattering, they'll revise their whole system. And indeed, if they have further experiments which show further scattering with regard to hadrons, then they'll say the quarks are not fundamental particles. So, this is what I've read, and I think it's really just a bit of a quick fix. I'm not convinced by it either. Thank you.
Yeah, I think that what you're saying is correct, between this dichotomy between baryons and leptons, and because they've kind of grouped it that way, they're kind of just, like I said, the elephant in the room, which is a gigantic thing that everyone's wondering about, but no one asks about, is, what is the relationship between baryons and leptons, and what's why is it you can't explain what electron is made out of, right? So I see Michael has a comment. Michael, you can go ahead.
Well, I have a different perspective. To elucidate reality, I go to the cosmos. I don't go to a physics lab, and I'm an etherist too, so that puts me even at a more of a different perspective. But in my model, electrons came from a preceding ether world, and with islands which were quantized, and the electrons were projected into a virgin ether, which was not quantized, not electromagnetized, had no atomic structure. And now we're trying to elucidate reality in a physics lab, which is the environment is atomically structured, quantized, electromagnetized, and it's different from the creational scenario, which is where you project an electron into a virgin ether, which has no quantization, and such an electron conceivably could set off a kind of chain reaction in which quantization occurs in like a chain reaction, and atoms appear, nuclei appear, slower mover particles like neutrons and protons appear as a result of the electrons, which are the smallest and fastest unit. And so I mean, you never see quark stars, you never see lepton stars, you do see neutron stars. So I think electrons, protons, and neutrons is what I'd focus on myself.
So would you be in the quarks fact or quarks fiction camp?
I'm in a camp where quarks appear as a result of physics experiments in an artificial environment, an earthly setting, which is highly quantized, highly electromagnetized, and atomically structured, and doesn't relate to the cosmic origin of reality, of what really originated the whole thing, which involves creational manipulation of using electrons, I believe. From islands.
Okay, well, I see Bill Lucas is here. So, Bill, so we're discussing the nature of quarks, and one of my assertions is that electrons are not made out of quarks, and mainstream would agree with me on that. And that the problem here is that you've got a theory, quarks, which can't explain all of the observed particles, namely the electron. So I think that's a big hole. And now the question is the electron fundamental? And my assertion is that in all of my research, every experiment that, I don't know, at least mainstream has done or attempted to do, has shown that the electron cannot be split up into anything. Now, I know that you believe in the ring model of the electron, where electron is made out of three things. So, Harry wanted to ask the question to you as to what experimental evidence we have of an electron being a non-fundamental particle. And we do have Bill here, don't we?
His icon went away. I don't know.
Oh, darn, I asked all that question, and although that was a fair question, right, Harry? Okay, so Mitch, you've got a comment?
Yeah, thanks. Yeah, I don't believe. I think quarks are fairy tales also, but I don't believe that the electron or any particle is fundamental. I believe in infinity in both directions, so I don't think anything has. I think everything can be broken down, no matter how small you get. It just goes on for infinity. But I think the quarks are kind of a misinterpretation. I think there's something there that they're measuring, but I just think their interpretation of it is way off. We need some new theories. I think we're back in the days where, I always like to say this, like the epicycles. The epicycles did explain a lot of things very good. It got more and more complicated, as time went on, and we discovered, different inconsistencies, and we had to make adjustments. But we made those adjustments using epicycles, and it got very, very complex, but they did explain things. And I think that's kind of what the state we're at today. We need to look at things from a whole different perspective.
Well, it's interesting you bring that up. So, like, one of the stories they have in this book is something called the November Revolution. See, now the problem in the development of quarks is that they predicted, there should be like this decay into a down quark, and that was not observed. So, as far as they could tell, quark theory was wrong, right? All the mainstream people had to say this can't possibly be right because it makes these predictions and we never see them. So what they said instead is that, well, if there's this other thing called like a charm quark, or strange quark, then that would fix the problem, right? Okay. So what they did, what happened is in this November Revolution was that they found a new particle called the J psi particle, right? And it just happens to theoretically been made out of one of these charm quarks, blah, 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 the thing that they needed. And since they found that particle, then that plugged the hole in the gaping hole in quark theory that was completely stopping it from being accepted.
Ah, interesting.
So that's just like an epicycle, right? It's like, okay, we know that, we can explain everything except there's weird things that go this way, and so we'll just explain that there's this other thing. We can just throw that in there, and then that fixes the theory. Now, in science, that's generally called an ad hoc theory, which is there's no actual reason to believe that these things actually exist, but its only purpose is to basically save an otherwise failing theory. So, but a lot of this book actually deals with that event, not that we actually found any direct evidence of quarks. I mean, there are some things in this book, like they'll say that in particle accelerator experiments, that if quarks exist, we cannot observe them directly, but they should theoretically produce like an experiment which will have 3 jets coming out of it. So we would predict that that's possible. Now, if you run enough accelerator experiments, we have seen these things, right? So we have never directly observed any particle being made out of 3 anythings, quarks specifically, but they would predict that you might be able to see these occurrences in accelerator experiments where you see these 3 particles come out of this particular type of experiment. Now, yes, indeed, they have seen those. It is consistent with quark theory, but the thing is that my main criticism about these kind of accelerator experiments is that if you watch enough accelerator experiments, as long as it's not forbidden, you will see every possible kind of result, including 3, maybe 4, 5, 10, 23 jets. But if you just see the 3 jet one, then you go, aha, it confirms my theory. But really, that's like saying I know how to win the lottery by basically picking every possible number and then saying I win, right?
Yeah,
I think that's.
Yeah, I have the same problem with the accelerator experiments too. Another along that same lines, I think that their assumption that all particles of the same particle are exactly the same too, I think confuses things, because once they see an event happen, once in a million times, they think, well, the same event, because it's the same particle, the same event happens to other particles, we just don't see it. Well, that might not be the case. I think, all particles might be slightly different, just like, from a distance, it might look like all the planets are about the same size or close to the same size, but they're all different. and some of them have moons and some don't have moons. And that could be the same with these particles. Maybe some of them have their own satellites and some of them don't, but they're so hard to detect. And once we detect evidence of a satellite on one, we say, aha, well, all of them must have satellites. Well, that might not be the case.
Well, I have a question about this. Okay, going back to what I said earlier, which is mainstream assumes there's only one solution to the set of experiments that they do. And they don't consider that there may be more than one solution. And are you saying that there may be more than one solution, or are you just saying that their solution is flat out wrong?
I would say their solution is flat out wrong. That's what I would say. Their taxonomy of particles can be explained by quarks. You know, you can take any particle that they've discovered and categorize it into
if you're going to assert that their solution is flat out wrong, then you have to produce the proof.
Yes, well, the thing is that I cannot disprove, just like you cannot disprove, anything, disprove quark theory, because, obviously there are a lot of people who believe in it, and they've done 50 years of work on this, and they go blah, 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 blah. So now basically, I cannot disprove that. Now which brings me to my other major point is, what are the alternatives to this, right? So if quark theory is not correct,
that's wherein lies the problem, which is that they assume that the way they do science, that they assume that their science is unique and only produces a unique solution. And so that process involves steps of elimination. So somewhere along the line, they eliminate all possibly other theories. And that means that the only theories left is the theory that they currently have, which is the quark theory.
Yes, that is what I would generally agree with that. But I would say that at some point they threw out the baby with the bathwater in adopting quark theory and ignored what the actual physical reality is. So,
well, from their point of view, they would say the experiments prove to us that quarks must exist.
Yes, absolutely, they do that. But I will first say once again my own opinion, my own theories about why I believe quarks are a fiction, because I believe that the observed experiments and the observed particles, all of them, can be explained in terms of just positrons and electrons. So instead of having,
you have a theory that you claim can do what they are doing with their standard model.
Yes, exactly. And I got into this very, very deep discussion on Quora.com with this guy about electrons, and he challenged me to, he's saying that, oh, well, positron electrons can't explain everything. And so I said, okay, give me something that can't be explained with positrons electrons. So he gave me the most complicated particle possible, which is like the charm sigma or something like that. And then I looked at its decay modes, which everybody knows what they are, and then decomposed it back down into what can only be positrons and electrons. So I'll show you that whole discussion there, because it was quite deep and quite interesting. So, and I think it's worth sharing with you guys. I should really actually write a paper on it, is what I should do. Just take everything that was discussed there and put it into a paper, because I think it would be quite interesting to see how that discussion went with.
So did he concede the point?
No, they never concede the point, but it'll be interesting to see how he argues around things. I mean, that's the main thing, about how things, because it's very clear how the arguments are made here. So, but this discussion was on Quora.com.
It seems to me kind of obvious that you can't be right by virtue of the fact that the logical progression of modern physics is such that they've ruled out all these other possibilities, and the only possibility is left is the one that they are promoting.
Well, I don't know that they've ruled out say even the theory that I'm considering. You'd think the theory that I'm considering, which is everything's made of positrons and electrons, would be, in fact, the first thing they would have thought of doing, really. I mean, because...
well, I guess what I'm trying to say is their view is that they've ruled out all the other possibilities, and one that exists that is consistent with the experiment, because
that's what
they've rolled out all the other possibilities.
This is exactly what they say. But my contention is that after a while, people just start parroting stuff. Parroting, meaning just repeating, but not really understanding what the origin or the basis for these things are. And when challenged, simply continue to parrot that exact same line that you just said, which is that, oh, well, all experiments confirm that quarks exist, blah, 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 without ever, so I would say, name 5, right? And they probably couldn't even name 1, really. But but this discussion started out with this question by somebody. It says, how can a neutron be converted into a proton and an electron if it is not made out of protons and electrons? So that seems like a perfectly reasonable question, right? We see the decay of a neutron, it becomes a proton, but see, a neutron is in mainstream is made out of like quarks, it's made out of 3 quarks, right? Some combination of up and down, right? So the question is, if that neutron is made out of quarks, then how can it become protons? So my answer being that, well, it's obvious to think that neutron is made out of protons and electrons, and that's what comes out of a neutron, right? Our basic logic usually says that if something falls apart into something, that it's made out of those parts that you see. So if we see a neutron falling apart in a proton and electron, it is most natural, most logical to think that there was a proton and a neutron in there beforehand. So I merely answered that, well, you think that's actually closer than you think. Maybe it is made out of protons and electrons, and it isn't made out of quarks. Okay, so this triggered this guy here, Eric Jensen, who is a cosmology PhD student. So he should know something about that. And he's saying this, no, is not consistent with observed reality. The quark model wasn't pulled out of thin air. It is thoroughly supported by data, which, is exactly what you just said there, Harry. This is their standard parrot response.
Well, you have to accept the assumptions if you're going to be a PhD candidate. If you don't accept the assumptions, the underlying assumptions, then you can't be, they're not going to give you a degree, because it's a club, and the rules of the club, require you have to abide by the rules of the club in order to become a member. So the rule is that you have to say these things and believe that they're true.
Well, this is what they all say. That what Eric says here.
Right. I just explained why.
Yeah, exactly. That's why they do that. Totally.
And in passing, I was going to remark, just as you were putting this up, Franklin, about the parroting and about, towing the party line and so on. It seems to me that the quark proposition was considered as a bit of a curiosity when it was first mooted. And it was really only after 1969, when Gell-Mann was awarded the Nobel Prize for his work in this area, that it became established dogma. So I'm really introducing a sort of a political element to this whole question of accepting the orthodoxy.
Well, that's quite right, Ian. I think you hit it right on the head. Once you've given a guy a Nobel Prize, you can't say it was wrong.
Yes, quite so.
Okay, we got some echo going on there. I think Jack just joined us. Make sure to mute your line so we don't get an echo. Okay, so there's your standard parrot line, not consistent with observed reality, quark model, blah, blah, supported by data. That's the standard. So I challenged them. I said, okay, show me the data that shows an isolated 1/3 charged quark. There is actually no theoretical reason why that can't be found, and lots of people have been trying to find a fractionally charged quark, but it has never been isolated experimentally. So all the experiments basically prove quarks do not exist. And then I mentioned that you can retreat into your ad hoc made-up explanation that they cannot be isolated. even though there's no theoretical reason why that can't, it's actually, then I go on to say, it's actually far easier to explain everything in terms of just positrons, electrons. So I have my own paper on this, which is quarks do not exist. And if you're interested in, why I believe quarks do not exist, you can check out that paper.
What was the response to that?
Yeah, okay, so that's just my little paper there that I said that go look at that.
When you said quarks can't exist because they've never been isolated, what was the response?
So here's his response, okay. Said, where did I suggest that existed? So that's kind of a strange response, that he's saying that, okay, well, that he's saying that the isolated charge can't, that the isolated charge doesn't exist. Now he's saying that there is a prediction of quantum chromodynamics that if we ever did detect an isolated quark, that physics would be turned on its head.
Yeah, right.
Which is saying that.
To me, I would think, Franklin, I mean, this is just my suggestion on this. The main thing, that problem I have with quarks, okay, I'm just going to say my main problem is that their electric charge is 1/3. Okay, which kind of throws the whole concept of electric charge out the window, because the electric charge is no longer discrete as one unit anymore. It's now 1/3 of the unit. Well, if your theory is correct, then electric charge should be 3 units and not 1. But they made electric charge 1/3 in a quark. So, they don't even have their own theory right. Where does 1/3 of a charge come from? No, it can't be 1/3. It has to be the unit of charge. And that means that all charges, electrons and protons, have to have 3 electric charges.
Yeah, well, I would agree with that. I mean, that is an inconsistency in observed electrical charge, right?
So the question would be, explain that to me. I mean, to me, that's the one thing I don't quite follow. I'm assuming their argument would be that because these quarks don't exist in isolation, then the 1/3 electric charge concept is purely a theoretical.
Yeah, I would say so. But the main argument here is that quarks cannot be found in isolation because they can't, is basically what they're saying here. And then there's the usual you need to go learn physics explanation here. This is the other thing that all these people parrot, and said that if you want to talk about nuclear physics or particle physics, you want to dismiss current theory, you first have to learn what the theory says and why people were convinced to accept it in the first place. See, they're basically saying, you're stupid, you don't belong to our club, go away, you don't know anything. This is what they always say. Instead of actually answering the question, which is, show me the data that shows an isolated 1/3 charge quark, because there isn't any. So instead of answering that question, they start dancing around it by saying that, oh, well, actually, we don't think that thing existed. And if it did exist, it would completely turn physics on its head. And then goes on to basically insult me about my knowledge in physics, which is another typical.
So that does seem like a contradiction. Why do you think they accept that contradiction? That, to me, that would be, I mean, I admit that there seems to be some contradictions in this whole quark idea. Unfortunately, saying that quarks don't exist and they're a fiction kind of is too much of a challenge to their belief system. And that's really kind of going to get you nowhere. You've sort of hit the nail on the head, which is if a quark can't be isolated, then it's just a theoretical, it's like an ingredient in a recipe that never really can be, that doesn't really exist as an ingredient.
Well, like I said, it's like a taxonomy. It's like it's a convenient way to categorize things. That it's like you set up a box that's got 10 slots in it, and you put everything into one of those slots, but the slots themselves don't mean anything. They're just a convenient way to organize things. So quarks either do exist, in which case there is actual 1/3 charge out there, or they're just a convenient nomenclature, right?
Well, why don't you say that? I mean, it seems to me that it would be easier to say, not to say that they're a fiction, but to say that they're, I'm
Convenient
not sure
nomenclature.
exactly what you're denying the existence of quarks, and then are you going to admit that they're a useful categorization, useful for creating models? And is that what you're admitting to, or are you just denying that they're not useful in creating models either?
Well, to the extent that they're useful to creating models, they're useful in creating the wrong models. So in that way, I don't even think they're useful for that. I mean, it's like the whole epicycle thing. It's like they're useful in characterizing the motion of the planets through epicycles, but epicycles just simply don't exist. So what's the point of doing that characterization? It's not the fundamental truth. And my presumption here is that quarks have become so well accepted that people do believe that they actually exist. So,
well, you have to realize that the quarks came into existence in 1969, right? I think we pretty much talked about that. The Gell-Mann got awarded the Nobel Prize, and then there was the J-psi particle, which occurred in, I forget exactly when that was. I think that was in the 70s. And most of these kids that are in college now that are being taught physics, that was way before they were born. So from their perspective, that's ancient history, and they're up to date on the latest knowledge, and they're being taught that which is actually correct. And questioning the existence of quarks is something that's not even in their world of experience. They're being taught they exist because that was proved before they were even born. And so they're not really that concerned about what happened before they were born. They're just accepting physics as it is because that's what's presented to them.
Well, exactly. But then again, we have this guy asking this very sensible question, because he's exactly the person you're talking about, who has just learned that, oh, well, protons and neutrons are made out of quarks. And then he found out, oh, well, quarks break down into protons and electrons. And they can see there's a contradiction here, right? So how can the neutron be converted into proton if there wasn't a proton in there to start with? So that's a contradiction.
Well, I was in college in first year physics in 1969, and I remember the professor telling us all about the electron and the fundamental charge and so on, and saying, oh, well, there's some recent research to talk about it being divided by into a third or 2/3. But he said you can forget about that. Don't worry about that it's for the moment. Now, however, the first conception by Gell-Mann and his colleague, the other chap who proposed it, was about 5 years prior to that. And this is the point I made earlier, which I think, Harry, you accepted, that it didn't really take hold until maybe the Nobel Prize was actually won. But the conception goes back to 63, 64. And the way I view it, and you mentioned this point about epicycles, is that the fact that there seem to be problems with this whole theory, and that we haven't found any isolated quarks, would seem to indicate that there's something fundamentally wrong with the theory. Just like if you don't have a proper physical theory of the solar system, well, then you can introduce epicycles and you can fix it so that you get the right results. To me, I mean, you took on this chap quite strongly, and he became very defensive. But one could have been a little milder and said, look, the fact that this thing seems not logical and that you haven't actually proved it by isolating these particles seems to indicate that there's something fundamentally wrong with your whole standard model, and you need to introduce these hypotheses, which are really no more than the epicycles of the solar system of the past.
Yeah, that's a very interesting comment. So here we go on with their challenges here, which is, So he's basically saying that there's these predictions of quantum chromodynamics that basically say that quarks can't exist in isolation. So I challenged him to explain why is that a prediction of quantum chromodynamics. And then we get some other things, which is they say that the QCD force gets stronger with distance, and it's like a rubber band, and once this force gets strong enough, so this is the explanation for why the quarks cannot exist in isolation, because they're connected by rubber bands, and that as soon as you get enough energy to break the rubber band to make an isolation, it actually causes the band to break, and therefore you still can't see the isolated quark because there's enough energy to make another particle that's not a quark. Isn't that convenient? Okay.
Well, this is similar to the theory of special relativity, where you just sort of invent reasons why the theory can't be wrong.
Yeah, so this is my second point here, is that, so I go on to explain to me why this just isn't an ad hoc explanation, which is tacked on when it became apparent that quarks could not be isolated. So the reason why we can't see leprechauns is because they are invisible. And the reason why we can't see quarks is because of color confinement. So the existence of this ad hoc hypothesis does not seem to stop people from searching for free quarks, which they do. Now, if there was some theoretical reason why fractional charges should not have been observable in 1964 when quarks were invented, why would we have put in so much effort forth in finding them? The problem here is that color confinement was invented to cover up the gaping experimental hole in the direct direction of quarks. So we have Bill here. So Bill, what do you have to say?
Poor Bill.
I have a question for you. First of all, how many of you have ever performed any experiment whatsoever in elementary particles with accelerators?
I don't have to. I've got the results of 30 years worth of experiments behind me.
Okay, so you don't understand,
Bill.
You don't understand how measurements are made.
I do understand how measurements are made.
Well, tell me, what do you use hundreds of detectors for just detecting one beam on a target? What
you have various detectors.
And
the easiest ones are
continuously. What are you doing?
But see, Bill, you're using the same argument here, which is that you're not part of the physics good boys club here, and you're not part of the priesthood. That actually isn't an argument against. That isn't an argument against anything. All you're trying to do is discredit credentialing, and there's no way I'm going to be able to come close to matching your credentials. So there's no contest in that respect. If you were talking about credentials, I have none. You have lots of credentials, but that doesn't say anything about the particular arguments that I'm making. I can still contend that quarks do not exist.
Tell me how you know there is such a thing as an electron.
Well, we know such things as electrons because we can make beams out of them. They hit screens. We can count their individual charge.
Wait a minute.
There's lots of things that demonstrate that electrons.
You've never been involved in these experiments. You have never done one. You are imagining many things which are not true.
Like I said, I've got 100 years, thousands of years worth of published experiments that I can refer to. I do not need to do any of them.
But you don't understand them because you've never done one.
No, that's not true. That's completely false.
Okay. Well, how can you detect an electron?
The easiest way would be to make a beam of them and fire it at a phosphor screen, and the energy deposited by the electron will show up as an individual point of light. This is how I typically detect electrons.
You can do that with 90 different types of particles. How do you know you have an electron?
Probably because once again, these are experimental results. But Bill, I think in mainstream, the existence of electron is not debatable. Electrons most certainly exist. It's one of the most best confirmed things ever. I mean, in the discussion, you know, email discussion, someone was saying, "Oh, well, we don't know electrons exist." Like, that's BS. Electron is one of the most best confirmed, you know, subatomic particles that we have. Like I said, you can detect them easily. I mean, that's how our CRT screens work. The Milton oil drop experiments show that their charge is quantized. I mean, there's most when you send electricity through a gas, it lights up the gas. We can see these directly with our own eyeballs in like there's a science exhibit at my science museum where we have like a cloud chamber, and you can see the little subatomic particles leaving tracks directly with our own eyeballs. We don't need any interpretation at all to see that those seemingly invisible particles are right there before your very eyes.
But all the charged particles leave tracks.
Yes, they do, and some of them are probably electrons. You can measure electron characteristics by putting them in magnetic fields. They will bend them in certain ways, and you can sort them out that way.
All of them bend too. All charged particles bend when you put.
Yes, and you can sort them out based on how much they bend.
Well, anyway, what I'm trying to say is that when the empirical equations of electrodynamics were developed, the concept of charge, and also in the case of Newton's laws, the concept of mass, were things that cannot be measured directly. And so
I would say that is directly false. I can step on a scale and it directly measures my mass, so that completely contradicts what you just said.
No, you don't measure mass, you measure weight. If I were to put you on a rocket ship and you step on the same scale, you're not going to measure the same thing.
I would say that's an irrelevant, just because you're saying that you can't measure mass, and I'm saying yes, you can.
Well, I'm saying that mass is an approximation to represent something that we cannot measure directly, just like charge is the same way. And so
we measure those things directly.
You know what these things are, but you really don't.
At the very least, empirically, we know how to measure those things quite precisely.
We don't.
We do.
No. Did you know that the weight?
But no, where is this discussion going to?
Entity is changing every year. Like we have these standard weights. Why are we replacing those standard weights with new definitions? And the answer is because our standard weights are not standard. They are not constant. They are changing. We don't know why they're changing. So we are using a new, and all the fundamental equations in modern science are now, our standards group is redefining them. And you don't realize why they're doing that. It's because we don't understand what weight is. We don't understand what mass is. And we're going to have to use a different definition.
So that's all very interesting, Bill, but please get to the point. So we're talking about quarks factor fiction. So what does what you just said have anything to do with that?
Well, the characteristics of quarks can be measured. Some of them can by scattering, the same way we do electrons. And we're able with the same, we can't see an electron, you know, you can't look at one with your eye. You're always using an experiment, and you don't.
You can see them in the cloud chamber. You can directly see them.
So, well,
if the individual electron goes zipping through the cloud chamber, it leaves a visible track. Or, you know, even the experiment that's in my science museum, you know, the electron goes zipping by. That's about as.
Now, is the track the electron, or is the track something that is disturbing the medium, the cloud?
Well, certainly it's disturbing something that's going through the cloud.
We know
so
that all
must be something.
Even ions do that.
Yes, there's something going in there. It's hard to characterize them when you're just looking at them, but certainly some of them are electrons.
Yeah. So the question is, what do we know and what do we not know? The current scientific community is saying these standards and these that we have made, that we've been using for commerce and scientific work and everything, they're not valid, and we are trying to define new standards. And so the NIST and the National Bureau.
Well, once again, this doesn't have anything to do with
starting to do that, and this year and in 2019, the new standards will go into effect. All your fundamental equations in science will change. You get that? Will change, because now our constants are different and we have a different definition. So,
for what?
For charge, for weight, all those things have changed. And
not by much, Bill. Maybe by 0.00001%, maybe.
We don't understand. If I take a standard mass and I put it in a vacuum in my museum, and I come back and weigh it at the same spot on the Earth, it weighs different every month and every year. Why?
So what does this have to do with quarks? What does this have to do with quarks, Bill? I just have to keep on bringing you back. Because,
I'm just trying to say we don't know any more about electrons than we know about quarks.
We know, you're saying we know less about electrons than we know about quarks. Is that
we don't know any more about electrons than we know about quarks. And you have got to convince us that we know more about electrons, but the standards group say, yeah, that's right. And we're putting out new standards. Haven't you read the scientific news? It's all over the internet.
Yeah, but I find it completely irrelevant. And it's like I said, it's changing the standard by so little that it's not, for all effective purposes, it's not a change.
It is a change because the idea behind the previous standard.
But that doesn't say that we don't know any more about electrons. I mean, you're talking about standards, and then we're talking about the existence of electrons.
The mass of the electron should be constant at rest, but it isn't. It's changing over time.
By the way, just a slight irrelevancy. I presume you're talking about the redefinition of the standard kilogram in terms of Planck's constant, which took place on the 16th of this month. Now that took 160 years to do. I mean, they've standardized on this platinum iridium weight in Sèvres, just in the south of Paris. But they agreed, obviously, earlier this month to redefine it in terms of physical constants. Yeah. So,
that's fine. I mean, they're just trying to define it in a way that on something that doesn't just like constantly change.
Yeah, and that could be reproduced in any laboratory theoretically in the world.
That doesn't. I mean, Bill's assertion seems to be that the weight of an electron changes based because they can't keep the weight of this platinum iridium cylinder constant, and I would say that's completely wrong. I mean, that has nothing to do with the mass of the electron, really, other than a definitional kind of thing.
How do you measure the mass of an electron?
You measure the mass of the electron by passing it through a magnetic field. The amount of deflection tells you what the mass is.
How do you measure the strength of the magnetic field?
By standardizing it and measuring it and say, okay, this much.
It's not standardized. We just changed the standard for it because it wasn't working.
I mean, although I still don't see your point here, is that I think we know a lot about electrons. We know a lot more about electrons. The existence of an electron is much more better established than the existence of quarks. Much better. I would not ever doubt the existence of an electron, and I would strongly argue against anybody who says that we don't think that electrons exist. I would say that that's completely insane if you think electrons do not exist or that we don't have adequate experimental evidence.
What do you mean when you use the term exist, I'm guessing that you mean material, fundamental,
like,
non-divisible, but you should be like specific, because some things are mathematical constructs versus being non-divisible. So we should try to be specific.
well, by exist, I would use the intuitive notion of existence, which means it's a ponderable physical object. You
Okay,
know,
but
like,
the Earth exists, but we know it's
a physically ponderable object.
the Earth exists, but we know it's divisible. It's not fundamental.
Yeah, so I wouldn't include any kind of a definition like that. Divisibility is irrelevant to my definition of existence. That is ponderable, it's detectable, it's separatable from the background. It can be tracked through time. That's the only thing that determines existence. Just to be more precise. But getting back to this discussion here about quarks, so the argument is that quantum chromodynamics exists. There's this funny force that acts like a rubber band.
Well, it looks to me like your argument is you don't find this to be convincing. And,
no, that's my
because you
response.
don't find it to be convincing, you just deny the whole theory. That seems to be my take on it.
Yeah, basically, I say I don't find that convincing because my comment here is the very concept of a force that gets stronger as the particles which create the force get further apart seems absurd on the face of it, right? Here we got a force that interacts between these particles, gets stronger as the particles get further away, right? Now, that's absurd because it's like we know interactions are stronger between things which are obviously, whatever's interacting between them can get closer and is less diluted. But somehow they're saying that this interaction gets stronger as they get further away, which completely contradicts all of our experience so far. It doesn't seem to make any logical sense that I say that it is the very definition of a made-up force. It is just a matter of convenience that we twist the theory around to make the very detection of the basic fundamental quark impossible. So really, the existence of a quark can never be proven. And isn't that convenient, right? So basically, we've proven that the quark can never be seen, even though that would be the most direct evidence for it. But that just been shown to be impossible.
Well,
so
that
there's
argument,
no
to me, that argument would say you can't claim that the quark is a particle, because if you can't isolate it, by definition, a particle is something that is discrete and can't be part of something else. So therefore, a quark can't be a particle. So you seem to be saying that a quark's not a particle.
Well, I'm saying
necessarily that it can't exist.
What you said before, which is that if a quark, my next sentence here is, so if you believe in quarks, then logically you might as well believe in leprechauns as well. Since you can never isolate a quark, you can never disprove it doesn't exist. So is it good to have a model that cannot be falsified by experiment? And I don't think so.
Okay, but you're using the definition that the quark is a particle.
Yeah, quark is a particle. Quark is a particle, even in mainstream.
So you're basically here saying that a quark is not a particle. The quark doesn't exist as a particle.
I'm saying that a quark does exist as a particle. It should be detectable.
Well,
but they're saying that it can never be detected, so we can never confirm it that way.
So it can't be a particle. I can see that by that definition of particle, it can't possibly exist.
No, even in mainstream would admit that a quark is a particle. If they wouldn't say
I don't see how they can say that if it can't be identified as a if you can't separate it and make it into something that's discrete that you can measure. It's not a discrete something that is its own identity separate from something else. Then it's not a particle, it's something else.
No, they do say it's a particle. Like I said, the color confinement argument is that the quarks are particles, but as soon as you try and separate them, and you give enough energy to separate them.
Well, it can't be a particle if you can't separate it. That's, you know, that. So they're somehow fudging the definition of particle.
Well, I don't think the definition of particle has to do with even separational. At least that's not part of my definition. But they're just saying that as soon as you get two quarks far enough away that they might be separated, that adds energy to make some more quarks so that they can't be separated. So
the idea, as I understand it, the concept of a particle is that it's discrete in a topological sense, which means that you can separate it from something else.
Well, they do say
if you can't separate something from something else, then you can't say that it has a discrete existence. It can't exist. So it can't be a particle, because a particle is something that you can enumerate by saying this is the particle and it's not part of something else.
Well, I mean, they do say that because there is good evidence in protons that there are 3 scattering centers in a proton. So definitely a proton is not a fundamental particle, because we can see these 3 little things buzzing around on the inside. So in that way, and mainstream thinks those things are quarks, right?
All right,
so
well.
In that way, you could consider that as a way of saying that, you know, they're not, but you can't take the individual quark out of the proton. But from scattering experiments, we can see there are 3 scattering centers there. And so that is one of the arguments they would say, but I would simply say that those aren't quarks. I would say that those are 2 positrons and an electron. Those are the 3 things that you're seeing inside of a proton. Although I know Bill.
So you're going even further and saying that quarks don't exist even as a concept of something that exists as to form the structure of hadrons.
Yes, they're about as relevant as epicycles are to the, you know,
all right.
geocentric
Going
theory.
back to what Bill was saying, Bill, I think, raised a key point about, you know, what is it that you're saying, you know, what is mass, what is charge, you know, what is an electron, you know, and it turns out that these definitions to a certain extent are circular. Is that what you're saying, Bill? I'm not really sure exactly what you're, you know, the discussion kind of got confused. Could you sort of?
Yeah, let's just take positronium. This is an electron and a positron. They're coming together and they form a bound system. And what does it happen to it? It disappears and you get two rays of light out. So what happened to the mass? What happened to the charge?
Conserved.
Conserved? Well, that's your idea, but you can't see it. So are you saying
because it's conserved?
Since you can't see it, it doesn't exist?
We could see it with proper experimentation, which we have not yet done yet.
Hold on, Franklin. This is an interesting point that he just made. And this is one of the things that's kind of always bothered me. And how does mainstream deal with this issue of what happened to the charge?
Well, mainstream says that the charge was annihilated. See, this is their.
Please, Franklin, I ask you not to butt in. I'm sort of trying to get Bill's take on it. And you can.
Yes, Bill, go ahead.
Well, mainstream, believe it or not, doesn't formally believe that mass or charge is a separable property of particles and of matter, and they're all related to wave structures, and so in quantum mechanics, you know, you've got waves, and so you really don't know. We've assigned things to charge and to mass, but and we put them in equations, or put a letter that represents them. But the modern science does not confirmed that we really know what that is. In other words, when you have any theory, you have certain assumptions and ideas associated with it, and you don't know how to confirm those. And so the fact that positronium disappears to 2 rays of light, and the charge disappears and the mass disappears, and that is bothersome. And then the amount of the light, the energy of the photons coming off. By the way, photons don't exist either. But anyway, the energy of the photons is equal to the total energy of the electron and the positron that were bound together. And so, as far as we can tell. And so that means that energy is more important than mass or charge. And so...
Does any of that make any sense, Bill? It doesn't make any sense to me at all.
Well, it's a problem for you, Franklin, because you're saying that electron and positron are fundamental, and then Bill's just presented a refutation of that, and he's saying that, as I understood him to say, energy is the fundamental.
Yeah, and that's completely wrong, because energy cannot be fundamental. Energy is like me shaking my hand around, and it has no reality compared to, say, my hand.
Yeah.
So, I mean, my alternate explanation for that is that when the positron and electron come together, they form a new neutral particle. So where does the charge go? It's neutralized. The positive charge and negative charge of those 2 charges still exist. It's still 100% conserved. But when you put them together in a new particle, you get a new particle which is neutrally charged, which cannot be detected because it's in a sea of these exactly identical charges. And that explains where the charge went and where the mass goes. The mass, I would say, is always conserved. I mean, we want to say logically that when I have a rock, that it, no matter how much I break that rock up, it's still going to be, there, right? It's not going to disappear, and most certainly is not going to turn into energy. I mean, how can something as ponderable as a rock turn into energy, which is just basically me shaking my hand in the air? It's just not going to do that. Or the reverse.
Well, let's let Bill talk for a minute here.
The reverse is even more. If I shake my hand enough, will that turn into a rock? I think,
Franklin, here's my point. Now, this is why I want to hear Bill's response. You're kind of interrupting. I think Bill's hit upon a pretty important point here in what he just said, and that is, you would assert that there's these particle entities, electron and positron, that are fundamental, and but they disappear when this reaction occurs that Bill's pointed out.
They don't disappear.
Okay, so there's a disagreement. Well, okay, so there's a disagreement there, and let's just let Bill. I'm curious as to what Bill has to say.
Well, I was talking about how experiments are done, and we use hundreds of detectors. So when we make positronium, we have hundreds of detectors. If there was any motion of electron positrons of any sort going away from positronium when it disappears, we would detect them if they had any kind of charge or any kind of mass, but we don't detect them. And the concept of things canceling out, like charge or is a concept that's related to waves. It's not related to physical particles or billiard balls or something like that. They don't have that type of feature. And
they obviously do, Bill.
They don't. I don't.
If I take a helium atom
and had 2 balls disappear.
If I take a helium atom and I remove the electrons, we can see that helium atom is now positively charged.
That's a wave function feature.
That's not a wave function. That is a simple addition and subtraction of charge, having nothing to do with waves.
Well,
well, I don't think that you believe much in waves, Franklin, so that's kind of presupposes your position on that.
Well,
you
I
think
believe
that things are made out of particular...
to propagate. And that's only common sense.
The other thing you have, Franklin, is the electromagnetic field has tensile strength. And
yes, and I exactly predict that. Yeah, you will totally have tensile strength. That's not a problem. That's a strength in my theory.
Arthur Compton and Winston Bostick showed that the
yes, my theories absolutely predict it must have tensile strength.
Solitons in the field are not the source of the field; they are merely a wave structure in the field. And the source, the electron, is not the source of the electric field around it. The source of the electric field around it is the field that has tensile strength coming from all different parts of the universe. And
well, that's about as backwards as you.
You're assuming that the electron has a property called charge, and that it's its own property, and that the field is due to its charge, instead of vice versa, which is what.
No, Bill, that's just completely backwards.
Well, hold on. Let's not deny what Bill has to say.
I'm not denying it. I'm just saying it's completely backwards. It's like taking the entire universe and making it work in reverse order, or just believing in the same thing as believing in geocentrism. It's like, well, yeah, you can flip the entire universe around, but it doesn't make it right.
I think the bottom line is that you've made certain assumptions, Franklin. And as Bill pointed out, theories involve assumptions that can't be proved or disproved. And so there seem to be some that you've adhered to, and we can sort of see when you respond to what Bill says that, you have different set of assumptions that you're adhering to. That's okay. But right now I'm trying to pin down what Bill's views are. So Bill, as I understand it, what you're saying is you're saying that charge isn't really a thing it's a property of the field that's assigned to the particle. Is that correct? That's kind of what I'm gathering that you're saying.
I use the example of the tornado or the cyclone,
right?
Where you've got a funnel and you call that the cyclone, or you call it the charge, or whatever we're going to call it. But you really know, if you look at it from a satellite in space, that it's much, much bigger than that. And so you know that is an approximation. And so,
I totally understand that analogy. It's like in the eye of a hurricane, there's like nothing, right? Because the hurricane is not being caused by something in the eye of the storm. Obviously, there's nothing there. But I'm just would continue to assert that is exactly backwards to what is really going on, which is, I think most of us think, because we see the existence of the electric field only in the presence of these specific particles, which are electrons, which are in fact ponderable in our experiments, that they are the cause of the field. So I would say, in the tornado explanation, that there would have to be something spinning around, causing the wind to whip up around it. And that's what I am saying, that the electron is this thing. It is the generator of the field, which, like I said, is diametrically opposite of what Bill is saying. I'm saying that the electron is, in fact, the generator of the field.
Okay, so from your point of view, the electron is a particle that has a discrete existence.
Yes, an electron is definitely a particle, has a discrete existence. It is the generator and the source of the measured electrostatic field around it.
So your solution to the wave-particle duality is to insist that everything is particles.
Everything is particles, fundamentally. A wave is also a particle phenomenon.
So Franklin is going to go down on reality is particles.
Absolutely.
Okay, so that's your philosophical assumption and position.
That's right.
Position is different. I'm not really sure what Bill's view of a particle is, but I don't think Bill views the particle as being fundamental.
No, Bill's view has always been that the particles are made out of the field.
Right.
Bill?
And the field is the fundamental thing. Yeah.
Yes, the field, that's what Bill would say.
Okay, Bill, so what's your view about quarks, if we can jump to the topic we're discussing?
Well, if you're looking at an elementary particle, so-called, such as the proton or the neutron, it is made of substructures, okay? And those substructures have particular properties that we can measure. We can measure the charge and the mass and stuff like that of those substructures. And we can't form a beam of them, which we would like to be able to do, but we don't know how to do that. See if I can remember what I was going to say. The substructures have structure themselves. They're not the smallest structure. And the fact that the charge of this substructure is less than the charge of an electron or a positron, you know, like 1/3 or 2/3 of that, indicates that whatever the basic building block of all particles might be, it is not limited to a minimum charge of the charge of the electron. And so that gives us an idea that the quarks are actually complicated structures that are smaller than the quark from which it's made. And those structures are solitons in the field, and they have the property of a fractional charge. And it also raises the question, well, what is an electron if those measurements are valid for the charge of these substructures? And the smallest building block, if you want to talk that way, of particles would have a structure with a fractional charge of at least as small as 1/3 of the charge of the electron, and that suggests that the electron is not a simple particle, but it has 3 subparticles or substructures in it. And so that has ramifications, and one of the ramifications is it makes it possible to predict the mass of the electron. I don't know if you know it, but the standard model of elementary particles, the hardest particle to predict the mass of is the electron and the positron. And so this procedure or idea of concept that the electron is composed of smaller structures, which is more
I
prominent.
get from what you're saying, Bill, that you don't use the word particle, and you're very careful in not saying that. So these substructures aren't really particles. Is that correct? Would that be correct?
None of them are particles in the sense that they have some kind of permanence, and because the substructures, the fine structures, the solitons in the field, they tend to want to get together and make something bigger. And so that's what we see. We see the various, the 96 elementary particles that we investigate and think exist. They are have structures built from these solitons. And the fact that with an electrodynamic origin, field origin of elementary particles, enables you to predict the properties of all the observed elementary particles. Observed meaning we can form beams of them and scatter off of it and all kinds of things like that. The fact that we can do that with no adjustable constants. All we are doing is changing the geometry of the structures. In other words, the various structures have certain geometry, and the electromagnetic field has what's called chiral symmetry, so and spherical symmetry, two types of symmetry. And if we use that symmetry and look at the structure of all the elementary particles,
can we get back to like
your positron model cannot predict all the properties of all the elementary particles that we observe and we can form beams of, just like the electron. We know just as much about those elementary particles as we do electrons. And yet we have no theory that can predict these properties. The Standard Model cannot do it either.
Well, what is your bottom line on quarks, Bill? Are they fact or are they fiction?
Of certain elementary particles like the proton and the neutron. It's a substructure. It's not an independent structure because they always occur, quarks always occur with multiple quarks in a bigger structure like the proton or the neutron.
So in your scheme of things, quarks are facts.
Quarks are structures. They're structures that have chiral and spherical symmetry, and they can be predicted just on the basis of geometry. And that's why the ancient Greeks put on their academies, let no one enter here ignorant of geometry, because they believed that all the universe was determined by geometry, and the geometry was of the basic building block of all matter, which they called monads. And that was in effect for 3,000 years. That people believed that type of approach, and now we have changed that. And if you subscribe to my newsletter, Common Sense Science, you'll find out why we changed it and what happened. We changed it.
Okay, Bill, but I guess the real question here, the bottom line question is, are quarks particles or not?
Well, what we call elementary particles, none of them are particles. They're all, from a field point of view, they're all solitons. And solitons only form structures, they don't form elementary particles. So the elementary particles are made of multiple structures put together.
Well, I think the real issue from my point of view, my take, I'm going to be real radical about this, and I'd say basically the main thing that you're running into here in this whole discussion is that mainstream talks about elementary particles, which are discrete objects combined to form other objects, and it turns out that theory doesn't seem to work, that we don't really have fundamental particles at all, really, and quarks are certainly not particles at all. They're components of what we consider to be particles. So quarks really can't be particles. That doesn't say they don't exist, though.
Yeah, and quarks are not simple. They're complex, because when we scatter off of quarks, we can see the interior structure of a quark, and we can see that the charge is quite different from the concept of particles having a charge of one charge of the electron or two or three or something like that. It isn't like that. It's smaller. And so how can a structure made of multiple things have a smaller charge than that of the electron? The electron can't be used to make that type of a structure, and because it has too much charge. And then the charge of the electron is not a permanent feature. It disappears. And so does its mass. And so neither charge nor mass are fundamental quantities in nature. They are temporary structures or values that they have. And so we see that, and it's and also if we have positrons and electrons in the universe, they'll be attracted to each other and they'll all disappear. Why is it that we have electrons? Why haven't the positrons gotten rid of all of them? They do in space, eventually. And why isn't that everywhere? And so that's another question.
They are everywhere, Bill.
And the electric field is the only thing that we have measured everywhere. When we go out into space, particularly outside of our galaxy, our solar system, we reach areas where we can't find any electrons, but we still have the electric field.
Well, I would object to that, because I think I would prefer to give some status to the magnetic field.
Well, electric magnetic field are equivalent in some sense.
Correct.
Okay, so let's. So does that answer your questions? I mean, I would say that Bill's and my conceptions of how the electrons work couldn't be more opposite, really, as far as the contrast goes.
I would say basically the problem, this discussion sort of illuminates the problem of when you start calling things particles, then you run into trouble because the quark can't really be a particle because it can't be separated. So it can't be a particle, but they want to make it into a particle because everything that they're talking about has to be quantized and therefore has to consist of particles. So, you know, that theory, the assumptions they're making about the structure of things being particulate and talking about and using the word particle is either wrong or misleading.
Well, maybe you don't even have to talk about, say, particles. I mean, we're just talking about quarks, fact or fiction. Okay. So maybe they could call it something else. They could call it a quasi-particle or virtual particle or.
Yeah, but you're still running into the problem. Bill uses the word structure, which I think he says them very carefully.
Yeah, so they says quarks is a structure, right? It's not, you know, not necessarily. That's just another way of. But all these things seem rather complicated. But
well, obviously you have the problem of waves and particles, the duality of waves and particles, which we touched on earlier.
Well, I don't have a problem with
some people want to fit everything to be a particle, and some people want to fit everything to be a wave, and they sort of, you know, but you got this duality problem, and this duality problem is sort of biting you in the butt when it comes to quarks because they can't be isolated as particles, and so therefore they can't be a particle because to be a particle it has to be isolatable, and so, you know, so they can't. So quarks can't actually exist as particles. I mean, that's my take.
I think they can't actually exist because they don't exist. They're epicycles, is what I would say. I mean, they can't exist as a particle because they make no sense as a particle, and they just simply don't exist. So that's what I would continue to assert. And
well,
I'm saying
I can understand that from your point of view because, you know, a particle implies something that's discrete that is put together as a component of something else. And so you have, you know, 1 plus 1 of these and 1 of those, and they go together and they form something else. And that formula doesn't seem to be a very good formula way of talking about it.
Well, I'm arguing that this whole quark theory is a mess. So my comment here in the discussion is I think physics is just starting to come with grips with the feeling that there's something terribly wrong in our quantum mechanics model. The 6 quarks and strangely colored terms not model, and you just make up more quarks as you go along. This is looking more like Alice in Wonderland than any sensible physics. This is just a baling wire, duct tape, rubber band mess of ad hoc hypothesis piled upon ad hoc hypothesis. Sure, it works, but what a mess. This is also the hallmark of an all
But all of physics is like that, Franklin, I'm afraid.
Yes, it can never be disproved because
everything in physics is like that. All of science is like that, you know. There's, you know, science is, that's what science is. It's a cobbled together set of beliefs that, you know, if you have to create some kind of separability criteria, you know, and say, well, you know, we avoid this contradiction by, you know, applying this principle, and, you know, and then science is just riddled with that sort of thing.
Well, let's see what Eric's response is to all of this. I'm saying that this is total ad hoc baling wire situation. So he's saying that that why is this not an ad hoc theory? Because it's a direct consequence of the theory. Well, only a direct consequence in the sense that if it's not true, then this theory is completely false, right? But they say it's as old as QCD is not something that was tacked on later. Well, I'm not sure that's right, but until, you know, when it became clear that these things can't be isolated, because I think the history is that people tried to isolate these things. They couldn't isolate these things, and so they came up with, you know, color confinement to try and explain it, which once again I think is ad hoc, right?
I wonder, have you addressed in this correspondence with Eric or elsewhere, Franklin, the widely differing masses of the different types of quarks, and therefore one could conceivably say that they're not separate particles. There are 6 different types of particles, instead of calling them all quarks, because they all have very differing masses.
Well, I mean, I don't know whether this is relevant or not, but, you know, whenever I say that, say, a proton is made out of 2 positrons and electrons, people say, oh, well, the mass of that is like way less than the mass of a proton, so that can't be right. But the fact of the matter is, mainstream has exactly that same problem, that, you know, given the theoretical masses of quarks, that is also way below the mass of a proton, right? You just can't add up the masses of quarks and come up with the mass of the composite particle. It's just way below. And so they have some other ad hoc explanations for saying, well, the mass isn't actually due to the mass of the quarks, it's due to the mass of the gluons, and they invent a couple other things to make that up. So, but that's the only thing I really know about the mass of individual quarks, in that they don't add up to the observed mass of the composite particle, not even close.
And they claim that if you add in the masses of the gluons, you do get the total mass. Do they claim that?
Yes, they claim that if you add on the mass of the gluons, that you'll. But once again, ad hoc theory on top of ad hoc theory, right? It's like they could have said, well, we're going to add Donald Duck onto the mass, and that's where it comes from Donald Duck and Mickey Mouse and Minnie. That's where it comes from, right? They just didn't call it that. They call it gluons, which could be substituted exactly with Mickey Mouse, and it would mean the same thing. Okay. That's how you tell an ad hoc theory. That whatever they're talking about, you could substitute it with the word Mickey Mouse. Then you can see that it doesn't mean anything.
Well, I don't really see calling something ad hoc as really being, you know, because the way science is, it's all ad hoc. It's all, you know, oh, we found this experiment, and so now we have to figure out how we're going to fit that into our system of thought. So you could say the whole thing is ad hoc, you know, by a certain definition of it.
Well, I think that there are ways to have theories which don't have to have these ad hoc things. Like you find a very simple theory, and it stays simple, and it explains unknown or as of yet not measured experiments. Then that is the hallmark of a correct theory versus an incorrect theory that has just add-on after add-on after ad hoc.
Well, I would say, basically, based on this discussion so far, I would say that the concept of a quark as a particle is completely wrong, and because a quark can't be a particle by, you know, they admit that a quark can't be a particle, so you know, it's just not a particle, and so you could be right in saying that the quark as a particle is a fiction. I would tend to agree with that. But we don't know what this thing is. There's apparently something that, as Bill says, a substructure. There's apparently something that's there, and it's gotten the name quark, although you can't really separate it, and so therefore it really can't be called a separable thing as a particle.
Well, I don't even think we should play around with even that line of reasoning, because I believe that this entire enterprise of quarks is
from what
completely
I
wrong.
gather, you want it to be a separate, that the thing that goes inside of elementary particles has to be a separable particle.
Yes, absolutely. I believe that everything has to be a separatable particle, which is what we see. So, I mean, this discussion...
Well, apparently that's not the case. So quarks really are not particles. I think that's...
Well, they just... opinion continues to be that they just don't exist. They're epicycles.
Well,
You couldn't even be discussing them.
obviously they can't exist because they can't exist as particles.
No, they can't exist, and they can't exist as particles. That would seem to be
By your definition, you won the argument, in my opinion, by the definition that you're using. I mean, you won that argument because your definition, that they don't fit your definition. Now, the question kind of boils down to is, does the guy on the other side of the argument, does he have a definition that's suitable or not?
Well, the thing is that he continues to just parrot the mainstream line, which is we have experiments, everything's confirmed, it has these certain properties, and because it has certain properties, we can't be a. Which I call BS.
Admission that they don't know.
I call BS on that. So I challenged him. Okay, you show me a particle that cannot be explained by a positron-electron combination. So this is my assertion. My assertion is that any particle you can show me, I can break it down into positrons and electrons, which is the more simpler, in my opinion, view of how everything. So I say a neutron is in fact made out of a combination of positrons and electrons. A proton is made out of a combination of positrons and electrons. All of these exotic particles are positrons and electrons. So he gave me like the hardest thing with this 2+ baryon, which is a charmed sigma. This thing has a double positive charge, 2+ charge. And so he challenged me to explain a charged sigma, which is this ridiculously complicated particle. And I applied the principle that an object is composed of the object that it decomposes into, which I believe is very logical, right? As I said, our intuitions say that. So if you accept the concept of particle as, everything is made of particles. That's everything is made of particles. That's your unprovable assertion that's based on philosophy. Yeah, that's one of my postulates, that I believe that everything is like this Lego brick structure, and that eventually everything breaks into little particles, and eventually you'll get down to the one little particle that can't be broken up, and that is the logical assumption that I'm presuming.
You have the difficulty that your electron and positron have to be composed of something else because they disappear in the positronium example that Bill gave.
No, absolutely not. Absolutely not. The positronium example just shows that the charges are neutralized in a fashion where we experimentally have difficulty seeing it. But the positron and electron still physically exist. They're never destroyed. They are never.
So you're saying they go into the ether, I think, as I was told.
Yes, they go into the ether. It's as if two hydrogen and an oxygen atom met in a glass of water. They would react. You would see.
Okay, I got it. So you're I understand, that you think that what you're saying is consistent on the assumption that everything is made out of particles. So your assumption, your fundamental assumption is everything is made out of particles, that nothing, waves are an illusion, I would assume, in your view.
No, waves are mediated by particle mediums.
Okay.
They are phenomena above particles, as a layer of
that means.
But even leaving aside for the moment this question as to which came first, I call it the chicken and egg problem.
Yeah, exactly.
It might be nice to take the electron positron model, as a very neat system. And you, Franklin, may be able to explain how every construct can be shown to be so by the positron electron model. But I would submit that doesn't necessarily mean that it's true. That it is basically representative of reality. It may be simply a model, and you may have some other model which unfortunately might be more complex, which could describe the system.
Well, that's what we're
here
to
argue. To show that it works. You'd have to go a bit further.
Well, I would say that this is what we seek here at the CNPS, is that we are seeking the models which make most sense to us personally, since most of us are incapable or have the resources to, I don't know, prove these things. But the first step to reality is actually getting to a theory which is at least self-consistent, that doesn't require a lot of ad hoc hypothesis, that matches our intuitions about how the world works. So,
well, you have to have the ad hoc hypothesis that the electron and positron aren't annihilated in the case of in the case that Bill discussed. So, I would, the objection to that would be that's just ad hoc. So I don't really, I think you need to be careful about the word ad hoc.
Well, the thing is that I didn't have to add that on. I mean, my basic theory starts with that there are positrons and there are electrons, and that we are surrounded by a sea of those. That's basic. Now, anything I add on to that might be ad hoc. Okay? But in order to explain what's happened in the positron-electron reaction, that falls immediately out of those two assumptions, right? I don't have to add anything to explain that. It's like, yeah, the positron-electron are going to come together, form the positron, and then they're going to be disappear into the sea. That's my basic presumption.
Yeah,
I don't have to.
Your opponent could very easily argue that the assumption of the electron-positron sea is ad hoc. And you
that's
brought that in to explain why they don't disappear.
That's not an ad hoc. That's actually, all theories have to start with
ad hoc. What my point, Franklin, is ad hoc is a perception of the person on the other side of the argument.
No, it isn't. Ad hoc does have very particular characteristics.
I got to be honest. I got to be honest and say, in my opinion, your theory is ad hoc.
You can do that. I mean, but I don't believe
the whole thing is ad hoc. I just think it's all ad hoc. You got little green gremlins and leprechauns running around your whole theory. So
I don't have any gremlins. I don't have any leprechauns. I don't have any.
I think it's full of them.
No, all I have is starting with electrons and positrons. As long as you accept the existence of those,
you don't realize that you're just inventing leprechauns. Okay.
No, I'm not inventing leprechauns. We know the existence of electrons and positrons.
All right.
If you don't accept that, and some people don't accept that, then maybe you think that's electrons.
Well, I guess I'm in that category. So you see.
But my point here, and in this particular discussion, is that he challenged me to show that even this most complicated thing, charm sigma, can be explained with positrons and electrons. And I'm not going to go through all of this, but I say, these are the decay modes of the charm sigma. It goes into like a plus pion, and then it goes into kaons, and then at the end of the kaon, at the decay change, we only have protons and various pions, and then the pions are represented as positrons, electrons, and if you go through this whole thing, I can explain this charmed lambda as starting out life as a collection of 24 positrons and electrons. Now, mainstream says that the charmed lambda starts out life as just 3 quarks, right? But yet, somehow these 3 quarks have magically morphed into 24 individually identifiable positrons and electrons. So my question was, does it make more? I mean, how is it that this thing just is like, it's like the Hydra where you cut off the heads and more just pop out, right? How is it you got something that starts with 3 particles, ends up with 24? So I would assert it is much more logical to assert that you started out with a conglomeration of 24 particles and things fell off of it. And that's what we observe as the decay chain. Because I think one of the intuitive tenets of physics is that we think that things do not come out of nowhere, right? So something which contains 3 fundamental particles cannot end up being something with 24 fundamental particles, right? So this is another major argument against quark theory, in that we have to have these magical multiplying quarks in order to explain all these decay chain sequences, when it's much more straightforward. And I think that the charm sigma has got to be the most complicated particle that they have on the shelf. So anything else would be easier. So in that way, I have denied his argument that I cannot explain everything in terms of positrons and electrons. And in fact, I can totally.
And did he accept that conclusion?
No, he just continues to say that I have already proven to you that electrons and positrons cannot explain it, even though, once again, this is the reaction of a parrot, which is to just simply keep on replying with it. But let's see, here's his responses. Is that you haven't answered the questions about how a charge sigma sticks together. Now, I'm not exactly sure what the relevance of this thing is, because I'm explaining what it's made out of, and later on I explain effectively that nothing is causing the charge sigma to stick together. It is just random ball of positrons and electrons that gets formed out of these accelerator experiments. It's just like if I throw together just huge balls of mud everywhere, it's like certain of them are going to form a clump that are 24 pounds or something. Right? It's random. Right? So there really is nothing holding the charge sigma together. It's just this conglomeration, what I said.
Well, you could tell him that leprechauns do it. I mean, they're saying that gluons do it, so.
Now he's saying that this principle of decay products starting to leads to internal contradictions because the same particle can undergo very different decay modes. Well, of course they can undergo very different decay modes. If you got a glob of 24 different particles, it will decay in every possible way that they're allowed to be glued together into pions and kaons and all those other things. Of course they're going to be doing that. So I'm not sure why he brings that up. So he brings this other.
It's a standard ploy of the establishment to say that things cannot be explained other than in terms of their theories, and therefore that proves their theories to be necessary. But I mean, I wouldn't go to those lengths. I might say to you, Franklin, your system is simple and it is elegant, but that doesn't necessarily mean that it is ultimately true. You need more than that. That's what I would have said.
Well, someone should be able to prove that, say a proton, some clever experimenter might be able to show that the thing that's actually in there is actually two protons and electrons. That's a physically conceivable experiment that someone might be able to do that.
I'm assuming that they've tried to do that, and that's not what they found.
I don't know. I mean, the thing is that quark theory is so prevalent that no one would even try to look. Now, maybe they did. Maybe some of the experiments that Bill mentions effectively do that. But
to me, the main flaw is they're saying that quarks are particles, and they obviously can't be because they can't be separated to be actual separable independent entities that you could say are particles. So they've kind of.
Now, it's interesting. Eric's response
they've kind of beat themselves up on I can see where as long as you don't say a quark is a particle, then they could probably get along. But assuming as soon as you say particle, it has to be separable. Okay, and since their theory says they're not separable, then quarks can't be a particle. They're something else. So for me, that just negates their theory right there. But, I'm sure their response would be that, well, language is imprecise and...
No, see, their response, Eric's response is, because since I've totally crushed his argument that I can't explain that this particle is made of positrons, electrons. I mean, I totally crushed that. His responses are in a series of other questions, right? This is the other thing. When you totally nailed the mainstreamers' objection, they then come up with this whole other series of other questions. So Eric has a whole bunch of other irrelevant questions, 1, 2, 3, 4, 5, 6, since that I have to now answer, but he does not ever admit that, yeah, I did it, man. I completely crushed his question about whether things are can be explained in terms of positrons, electrons. So he's saying, in short, not only are you declaring premature victory when it comes to the question of being able to assign electron and positron contents of particles, but you're completely missing any kind of model for how these particles behave and what their properties are. Not something that you'd be ignoring. if you study particle nuclear physics, and that's completely false. I mean, in my explanation, I go carefully down and explain what all of the observed, using all of their terms, you know, neutral pion, cation, plus pion, using all of their terms to show what this thing is made out of. So, you know, that objection is just not right. And then he asked a bunch of other irrelevant questions. But how can we smash together two protons together very hard and get a whole shower of particles coming out, which is not relevant to the quark theory. But I would simply explain that we're sitting in a sea of positrons and electrons, and when you put enough energy from a positron-electron collision, you will kick all those particles out, and that's where they come from, right? Now the mainstreamers have to say that energy is somehow magically converted into these particles, and that's even a harder question to answer with quark theory, I think. So so I go and I respond.
So, looks like you won. Looks like you won, Franklin.
No, I never win here. Okay. So,
well, I have a question for you. There are many particles that are lighter than an electron, like neutrinos. And
yeah,
so,
neutrino is I explain that as a wave phenomenon. It's a very particular quantized wave phenomenon.
But we can
therefore it has no mass.
We can make a beam of them, and we can do experiments with it. So it's
exactly, you can make a beam of neutrinos, which is just basically a very, very isolated electromagnetic wave phenomenon. See, the neutrino is like in a Newton's cradle, where you drop the one ball.
You're seeing all electromagnetic fields have to come from particles, so we have to use the electron to make those waves.
Yes, you do.
Yes. So how can we define the mass of something that's lighter than the electron when the electrons are making the thing?
That has absolutely no relevance at all. I mean, what does the thing that making it have to do with the thing that results? I mean, there's no required connection at all there, right?
No,
I'm telling you that if the example that you're giving,
if I have particles, like when I'm building a theory of the atom, the mass of the atom is the sum of the masses of the components.
Yeah, but not exactly. I mean,
yeah, but you can't explain that in your theory because your mass is an inherent property of the particle.
No, mass is not an inherent property of the particle. In my theory, the mass is actually an inherent property of the particle moving through the ether sea. That's what it really is. Because the mass of a particle, like the mass of an electron, depending on its environment, can be shown to change. So the mass of electron, when surrounded by, say, a sea of positive charges, is different than when it's surrounded by a sea of negative charges.
Well, if I have billiard balls on the table, and the fact that I have a lot of them around it doesn't affect the mass of the one I'm using.
Which is an irrelevant simile, because I'm telling you that happens with electrons, not billiard balls, which are large macroscopic objects surrounded by air.
You have a particle theory. Everything depends on the properties of particles.
Absolutely, yes.
Just like billiard balls do. So billiard balls don't take some of these properties that you need, because we have things that it cannot.
That's because billiard balls are not individual electrons. Now, a lot of things can be demonstrated with billiard balls, and I believe that that's true. But you just can't equate electrons and saying that they do absolutely everything like billiard balls, especially mass, because mass depends upon the medium which it is contained upon.
So I mean, your Lego model won't work for the properties of various structures because you're going to change it to be independent of that structure or largely independent.
No, I would challenge you, present me any contradiction to my particle model of, say, atomic physics.
Okay, well, what you
I
need
have not seen any.
To make a picture or some kind of description of the structure of all the observed elementary particles that we can make a beam of and perform experiments with. It's not all that are predicted. We have 400 that various theories say would exist, but of the ones that experimentalists can make beams of and perform experiments, we've got only 96. So you must be able to explain at least the 96 particles.
Well, like I said, I explained the charm sigma, which is the most complicated particle we have.
That's
So
only
presumably
one
else
particle.
is less complicated than that.
A particle. That's a you know, you need to be able to explain the complete set. If I had a theory of
yes, I'm saying I could explain this complete set. I just have to sit down and do it.
Planet in our solar system, was that very good?
I can explain the complete set. Absolutely, that's not a problem.
Okay, well, that's what you should do.
I mean, that's just a simple exercise of looking to see what it decays into, because really the only things that don't decay are the electron, the proton, neutron. Everything else, well, even the neutron decays. Everything else decays, right?
Right.
I don't even consider
It
those real
decays by multiple modes, and you got to explain each, not just
yeah,
one.
and I explained every possible mode and give motivation for why there are different decay channels.
Well, I'd be interested in seeing that.
Well, like I said, look at this paper that I have displayed here. This is one of my most complicated, detailed breakdowns of a particular very complicated particle. I show it breaks down into like the charm lambda and a plus pion, and it decays into a proton and a kaon and a plus pion, and that's just, you know.
And now, remember, a proton has 1,800 times the mass of an electron or a positron.
Yes, and I've explained that that the mass of
1,800 of
the composite mass has nothing to do with its individual components. Even in mainstream, it doesn't. That the mass doesn't have to do anything with the inherent mass of the individual components, because it's not a measure of any inherent property of the individual components.
But
the proton is a composite, larger object, at least
have mass. What causes the electron?
And it's has to push through this medium of positrons and electrons, and that's the interaction that determines mass. It has almost nothing to do with the individual components. It's only the result, the composite result of the electric charges and their interactions and how sticky they are against the background. It had nothing to do with the individual masses, the individually measured masses of the components. And that's something that you would only understand if you understand what the actual nature of mass is, which is an electrodynamic interaction with the medium, which I think you would agree with, except that, you know, the only thing that you're not getting is that the medium is actually made out of mass and charge. That's the only thing that although, like I said, you're looking at the world at almost the opposite way that I am.
Yeah, it looks like it's a circular argument that you're making.
I mean, the difference is as big as, you know, keep on bringing up, you know, the geocentric versus heliocentric, you know, world. It's just that cannot be more opposite, really.
Yeah.
They both explain the same thing.
How can a proton, which has 1,800 times the mass of an electron and smaller than an electron, how can it have so much mass when it's so much smaller?
Like I told you, I just spent an entire 5 minutes explaining to you that the mass of the proton has nothing, zero. See that? Zero to do with the mass of its individual components, because it's not a measure of the properties of those individual components.
But if it was
it can be 1,800 times.
And it's smaller, it's going to have less resistance to going through the media than.
Well, I don't believe that that's true. I believe a proton must be volumetrically at least 3 times as large as an individual electron. But eventually.
Experimentally, when we do scattering, we don't see that. We see it smaller.
Well, there are some experiments and I've seen that, but I disagree with the interpretations that those experiments are saying.
Okay, so you're if you don't like the experimental results, you just ignore them and do your.
No, I believe that the interpretations and anything you do at that level is all interpretation. That if I had the resources, I would probably propose another experiment showing that. Well, I mean, but the problem with the size of a proton is that, you know, what do you mean by size? like we can't even measure, say, the size of an electron, but what's most important is its sphere of influence, right? It's like, at what point do you get, you know, with the point where it actually acts as, say, a hard surface, right? Now, maybe there is no hard surface of that proton thing. All you've got is this massive electric field surrounding it, and that's what you're interacting with. Now, that could be as tiny as a pea or as big as a basketball, depending on, you know, what's your definition, because there's no hard surface to say what the size is. So I'm saying that you can't say that the size is smaller than an electron if you know, we have a hard time defining what constitutes the surface, right? So that's where, you know, that gets into why I would disagree with any such interpretations that the proton is smaller than an electron. I think that that's probably false. But it looks like we're getting towards the end of our discussion here. And like I said, if you want to go and you know, look at this, like I said, I probably want to go and like write a paper on this about based on this particular exchange, because I think it is interesting. And it let me see if I can put that. So I put that link there in the chat. So if you want to go and copy that out and scroll it away someplace, you can do that. Or you can just search Quora.com and search for the question, how can a neutron be converted into a proton and an electron if it is not made of protons and electrons? So I'm sure if you search on that, you'll probably find that discussion. So, but so that's our talk today. This discussion has been on quarks, fact or fiction, and I've been trying to strongly argue that quarks are in fact a complete fiction, and that you know, they're not even a useful nomenclature for describing particles any more than using epicycles to describe the motion of planets would be a useful nomenclature. It's just simply wrong and backwards to do so. And that I have argued that everything that's surrounding quarks is basically an add-on, ad hoc hypothesis, and that these things are all much more simply explained as combinations of positrons and electrons, which have a lot less theoretical problems with, you know, where they come from or how they exist and stuff like that. So that will be my summary today. All right, so thank you for participating, and this ends the meeting.